The journey of light from our planet to the nearest star system is a humbling reminder of our cosmic limitations. Even at the fastest speed known in the universe, a beam of light takes more than 4 years to reach our closest stellar neighbor. To traverse the entire Milky Way, that same light would need 100,000 years. This reality places humanity in a kind of cosmic confinement, with the laws of physics acting as the unbreakable bars of our prison. But what if those rules could be bent, if not broken? Recent scientific advances suggest that the dream of traveling faster than light may not be as impossible as once thought. Researchers are now exploring concepts that could propel spacecraft at speeds 10 times greater than light, transforming what would have been journeys lasting centuries into trips that could be completed within a single generation. In laboratories, the first hints of warp bubbles are being observed, and the energy demands for such travel, once thought to be utterly unattainable, are now being recalculated to levels that, while still extreme, are no longer completely out of reach. If you're intrigued by the possibility of rewriting the rules of reality, you're in the right place. Let's start by considering the fastest object humanity has ever built, the Parker Solar Probe. This spacecraft hurtles through the solar system at a staggering 190,000 miles per hour. Impressive as that may sound, it would still require 70,000 years to reach the nearest star. To put that in perspective, if the probe had set out during the last ice age, it would only now be approaching its destination. Our current technology leaves us crawling across the cosmic landscape, while the distances between stars mock our ambitions. Even light, which travels at 670 million miles per hour, needs 4.5 years to bridge the gap to Proxima Centauri. The Milky Way itself is 100,000 light-years across, making any attempt to cross it with present-day technology a journey that would outlast entire civilizations. Every star that sparkles in the night sky represents a place that, with our current propulsion systems, is utterly unreachable within a human lifetime. The Voyager probes, launched in the late 1970s, have been traveling for nearly 50 years and are now about 14 billion miles from Earth. Yet they haven't even fully escaped the gravitational influence of our own solar system. The stars remain as distant as ever, and we are like infants, barely able to crawl when what we need is the ability to sprint. The harsh reality is that space is not just vast, it seems almost designed to frustrate our desire to explore. The distances are so immense that even if we could travel at 99% the speed of light, interstellar missions would still require multiple generations to complete. The descendants of those who set out would be the ones to arrive, if they arrived at all. All of our propulsion systems, from chemical rockets to ion drives to nuclear engines, operate on the same basic principle: expel mass in one direction to move in the other. This approach is fundamentally limited by the so-called tyranny of the rocket equation. The more fuel you carry, the heavier your spacecraft becomes, and the more fuel you need to move that extra weight. It's a vicious cycle that quickly becomes unmanageable, with fuel tanks growing to the size of skyscrapers just to achieve a small fraction of light speed. Despite our achievements, sending robots to Mars, landing probes on distant moons, and capturing images of the farthest reaches of the observable universe, we remain confined to our own solar system. Unable to reach even the nearest potentially habitable planet, that world, just 4 light-years away, would require a journey of 25,000 years with current technology. Clearly, something fundamental must change if we are ever to escape our cosmic neighborhood. The universe is teeming with billions of planets that could potentially support life, yet we are unable to reach even the closest of them. The reason for this limitation can be traced back to equations written over a century ago by Albert Einstein. In 1905, Einstein's theory of special relativity established a speed limit for the universe. Nothing with mass can ever reach or exceed the speed of light. This isn't just a suggestion, it's a rule enforced by the very structure of space and time. As an object accelerates toward light speed, its mass increases exponentially, requiring ever more energy to continue accelerating. In practical terms, a spacecraft approaching the speed of light would become so massive that moving it even a tiny bit faster would require more energy than exists in the entire universe. This creates a paradoxical situation. The closer you get to the speed of light, the more impossible it becomes to go any faster. The universe allows you to approach the limit, but never to reach it. For over 100 years, this principle has stood up to every experimental test. Particle accelerators have confirmed that objects really do gain mass, and that time really does slow down as they approach light speed. The rules are absolute. Scientists have tried to find ways around these limitations. They've experimented with exotic propulsion methods, plotted complex gravitational slingshots, and even proposed generation ships where entire communities would live and die during the journey. But none of these ideas change the fundamental problem. Einstein's equations lock the door, and conventional physics can't find the key. If you try to break these laws, you risk unraveling the very fabric of causality, creating paradoxes where effects precede causes and the logical structure of reality collapses. Time dilation adds another layer of difficulty. Even if you could somehow reach 99% of light speed, time would pass differently for you than for those back on Earth. A journey that feels like 10 years to you might span decades or centuries for everyone else. You would return to a world that had moved on without you, your friends and family long gone. Length contraction further complicates matters. At extreme speeds, space itself appears to shrink in the direction of travel, making distances seem shorter to the traveler, but not to those left behind. For generations, physicists accepted these constraints as unbreakable. The speed of light was the ultimate limit, and nothing could surpass it. Teaching this became a cornerstone of physics education. Breaking the light speed barrier seemed as impossible as squaring the circle or making 2 plus 2 equal 5. Yet, some scientists refused to accept defeat. They began to ask a different question. What if our understanding of movement itself is incomplete? Accelerating even a small spacecraft to light speed would require more energy than is available on the entire planet, and then some. The mathematics are unforgiving. As velocity increases, so does the kinetic energy required, and near light speed, the energy demands become astronomical. For a 1-ton spacecraft, the energy needed to reach light speed is equivalent to the total annual energy output of human civilization, all consumed in a matter of seconds. Even nuclear fusion, the process that powers the stars, would barely make a dent in the energy requirements for interstellar travel at significant fractions of light speed. The challenge of interstellar travel isn't just a matter of building bigger rockets or finding more efficient fuels. It's a fundamental problem woven into the very nature of physics. Decades ago, ambitious projects like Project Daedalus imagined using fusion-powered rockets to reach a mere 12% of light speed. Even then, the design was dominated by enormous fuel tanks, dwarfing the tiny compartment meant for crew and cargo. The ship would need to carry 50,000 tons of deuterium and helium-3, and after all that, it would still take 2 decades just to reach the outskirts of the nearest star system. The payload, the part that actually matters, would be minuscule compared to the mountain of fuel required to get it there. Some theorists have looked to antimatter as a possible solution. When matter and antimatter meet, they annihilate each other, converting their entire mass into energy. This is the most efficient energy conversion process known, at least in theory. But in practice, we can only produce antimatter in tiny quantities, one particle at a time, using massive particle accelerators. Storing it is another nightmare, requiring powerful magnetic fields to keep it from touching the walls of its container and annihilating instantly. To produce enough antimatter to power a single interstellar mission would take thousands of years at our current rate of production. Other ideas have included solar sails, giant, ultra-thin sheets that catch the pressure of sunlight, or powerful lasers. These require no fuel, just patience. The acceleration is so slow it's measured in fractions of an inch per second, but over years it adds up. Still, to reach even 10% of light speed would take decades of continuous acceleration, and the sail itself would need to be miles wide, yet strong enough not to tear apart under the strain. No matter which conventional propulsion method you consider, the same wall appears. The faster you want to go, the more fuel you need. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more energy you need to accelerate it. It's a cycle of diminishing returns that engineers and physicists have been wrestling with for generations. Chemical rockets top out at a few miles per second. Ion drives can do a bit better, maybe 20 or 30. Nuclear thermal engines might reach 50. Even the most optimistic fusion designs only get you to about 3,000 miles per second, still just a tiny fraction of light speed. It's like trying to move a mountain by throwing pebbles at it. The real barrier isn't just technical, it's written into the structure of reality. Einstein's equations make it clear: to accelerate any object with mass to the speed of light would require infinite energy. Infinite isn't just a big number, it's a way of saying never. No amount of clever engineering or technological breakthrough can change that equation. But what if the problem isn't with our technology, but with our assumptions about movement itself? The urgency of this question is growing. Our planet is facing mounting threats, from climate change to the risk of asteroid impacts. When we look at our solar system for alternatives, the options are bleak. Mars, often touted as the next frontier, is a frozen desert with an atmosphere so thin that your blood would boil without a pressure suit. Temperatures plunge to minus 225 degrees Fahrenheit, and the air is almost entirely carbon dioxide. Dust storms can engulf the entire planet for months, and cosmic radiation bombards the surface constantly, thanks to the loss of Mars's magnetic field billions of years ago. Venus is even more hostile. Its surface is hot enough to melt lead, and the atmospheric pressure is like being 3,000 feet underwater on Earth. The air is a toxic mix of carbon dioxide and sulfuric acid. Probes sent to Venus have survived for less than 2 hours before being crushed and fried. The gas giants, Jupiter, Saturn, Uranus, and Neptune, are nothing but immense balls of gas with no solid surface, crushing pressures, and winds that can reach 1,000 miles per hour. Their moons, while intriguing, are frozen, airless, and bathed in lethal radiation. Even the most promising candidates, like Titan or Europa, present enormous challenges. Titan has lakes of liquid methane and a thick atmosphere, but the surface is nearly 300 degrees below zero. Europa might have a subsurface ocean, but it's buried beneath miles of ice in one of the most radiation-saturated environments in the solar system. Mercury swings between searing heat and deep freeze, and our own moon is a barren, airless rock. Every world in our solar system is either too hot, too cold, or too lacking in the basic ingredients for life. Terraforming Mars, for example, would require thickening its atmosphere, warming its surface, restarting its magnetic field, and creating breathable air, a process that would take thousands of years and technology we don't yet possess. The hard truth is that Earth is not just our home, it's the only place in the solar system where humans can survive without life support. If something were to render Earth uninhabitable, we have no backup plan. That's why the search for habitable worlds beyond our solar system is so important. The nearest potentially life-supporting planet, Proxima Centauri b, is just over 4 light-years away. The TRAPPIST-1 system, with its 7 Earth-sized planets, 3 of which might be habitable, is 39 light-years away. Kepler 452b, a planet remarkably similar to Earth, sits at a distance of 1,400 light-years. These worlds could be our future homes, but with current technology, they might as well be in another universe. Faster than light travel isn't just a dream for explorers, it's a necessity for the long-term survival of our species. Telescopes have identified thousands of exoplanets, dozens of which are in the so-called habitable zone, where liquid water could exist. We can measure their size, estimate their composition, and even analyze their atmospheres for signs of life. But we can't reach them. Proxima Centauri b, tantalizingly close in astronomical terms, would take 40,000 years to reach with our fastest spacecraft. TRAPPIST-1 would require 600,000 years, Kepler 452b, 25 million years. These numbers are so large they lose all meaning. They're not travel times, they're geological epochs. Astronomers can tell us the chemical makeup of planets dozens of light years away, but we can't send even a tiny probe to visit them in any reasonable time frame. The James Webb Space Telescope can detect water vapor and oxygen in alien atmospheres, but actually going there is still pure fantasy. The frustration isn't just scientific, it's existential. These planets could be lifeboats for humanity, refuges if Earth becomes uninhabitable, or even homes to other forms of life. Yet they remain forever out of reach, separated from us by an unbreakable wall of distance and the laws of physics. Even communication is limited. A radio signal sent to Proxima Centauri would take over 4 years to arrive, and any reply would take just as long to return. A conversation would span decades. Physical travel, as things stand, is simply impossible without a radical new approach to movement, one that doesn't just move us through space, but moves space itself. The idea that we might one day travel to the stars by bending the very fabric of space itself sounds like pure fantasy, but it's a concept that has moved from science fiction into the realm of serious theoretical physics. The breakthrough came from an unexpected place, a young physicist named Miguel Alcubierre, who was inspired by the warp drives of Star Trek. In 1994, Alcubierre published a paper that stunned the scientific community. His calculations showed that, at least on paper, it was possible to create a warp bubble that could move faster than light without violating Einstein's equations. The trick was not to accelerate a ship through space, but to manipulate space itself, compressing it in front of the ship and expanding it behind, creating a wave that would carry the bubble forward. Inside the bubble, the ship would remain stationary relative to its local space, experiencing no acceleration or crushing forces. To visualize this, imagine a surfer riding a wave. The surfer isn't propelling themselves through the water. Instead, the wave moves, carrying the surfer along. In the same way, Alcubierre's warp bubble would carry a spacecraft across the cosmos, with the ship itself never actually moving faster than light relative to the space immediately around it. This clever loophole exploits a subtlety in Einstein's theory. While nothing with mass can move through space faster than light, there's no rule saying that space itself can't expand or contract at any speed. In fact, cosmologists already know that the universe's expansion can outpace the speed of light at its farthest edges. Alcubierre's equations described a way to create a region of space with negative energy density in front of the ship, causing space to contract, and positive energy behind, causing it to expand. The result is a bubble that moves through space at any speed, potentially even thousands of times faster than light. The ship inside the bubble would be shielded from the usual relativistic effects: no time dilation, no length contraction, no crushing acceleration. To the crew, everything would feel normal, as if they were sitting still. The scientific community was both excited and skeptical. The math checked out, but the practical challenges were enormous. The biggest problem was the requirement for exotic matter, a substance with negative mass and negative energy density, something far stranger than antimatter. While antimatter annihilates with normal matter to release energy, exotic matter would behave in the opposite way, repelling rather than attracting, and creating gravitational effects that are the reverse of what we're used to. No one has ever observed negative mass in nature, and it remains a purely theoretical concept. Alcubierre's original calculations suggested that to create a warp bubble large enough to carry a small spacecraft, you'd need an amount of negative energy equivalent to the mass of Jupiter. That's more than 300 times the mass of Earth. Even if it were possible to create or collect such a substance, the energy required would dwarf anything humanity could ever hope to generate. Critics were quick to point out that, while the equations were valid, the ingredients were pure fantasy, like designing a car that runs on unicorn dust. Despite these daunting obstacles, some researchers began to look for loopholes. Could negative energy be created in the lab, even in tiny amounts? The Casimir effect, a phenomenon predicted by quantum field theory and confirmed experimentally, offered a glimmer of hope. When two uncharged metal plates are placed extremely close together in a vacuum, quantum fluctuations in the vacuum create a measurable force that pushes the plates together. This effect is a result of the energy density between the plates being lower than in the surrounding space, which can be interpreted as a kind of negative energy density, at least relative to the vacuum outside. The Casimir effect is tiny, only noticeable at nanometer scales, but it's real and measurable. If this principle could be scaled up, perhaps it could be used to create the spacetime distortions needed for a warp bubble. This is where Dr. Harold White, a physicist at NASA's Johnson Space Center, enters the story. White and his team began to explore whether the energy requirements for a warp drive could be reduced by optimizing the shape of the bubble. Instead of a simple sphere, they considered more complex geometries, like a torus or donut shape, and found that the energy needed could be reduced by several orders of magnitude. Instead of needing the mass of Jupiter, you might only need a few hundred kilograms of negative energy, still exotic, but suddenly not completely out of the question. Then, in 2021, something remarkable happened. While experimenting with the Casimir effect, White's team detected a tiny but measurable warp in space, time at the nanometer scale. They hadn't set out to create a warp bubble, but their equipment picked up a signal that matched the theoretical predictions for what a miniature warp bubble would look like. The effect was repeatable and consistent, not an artifact of the instruments or a fluke. For the first time, a warp bubble, albeit microscopic, had been created in a laboratory. The implications were profound. If a warp bubble could be created at the nanoscale, then scaling it up became an engineering challenge rather than a fundamental impossibility. The problem of exotic matter remained, but the psychological barrier had been broken. Warp bubbles were no longer just mathematical curiosities, they were real, observable phenomena. Other research teams began to revisit old papers and look for overlooked details, wondering if the answer had been hiding in plain sight all along. The Casimir effect, strange as it sounds, is a direct consequence of the quantum nature of empty space. According to quantum field theory, the vacuum is not truly empty, but seethes with virtual particles that pop in and out of existence, borrowing energy from the uncertainty principle and vanishing. Before they can be directly observed, these virtual particles create a faint background energy that fills all of space. Normally, this energy is uniform and undetectable, but when you place two metal plates close together, only certain wavelengths of virtual particles can exist between them, creating an imbalance that pushes the plates together. This force is minuscule, but it proves that negative energy density can exist, at least in a relative sense. If this effect could be amplified and controlled, it might provide a way to create the spacetime distortions needed for a warp drive without requiring vast amounts of exotic matter. White's experiments used carefully arranged capacitor plates to create regions where the quantum vacuum energy differed from the baseline, warping space-time ever so slightly. The effect was microscopic, but it was there. Scaling this up is a monumental challenge. The Casimir force drops off rapidly with distance, and creating negative energy densities across macroscopic distances would require entirely new materials or quantum technologies. It has not metamaterials, engineered substances that can bend light and electromagnetic fields in unusual ways, or even quantum computing techniques to control vacuum fluctuations with unprecedented precision. Others speculate that dark energy, the mysterious force driving the universe's accelerated expansion, might be related to these vacuum energy states and could be harnessed for warp field generation. The possibility that we might one day manipulate the quantum vacuum or even dark energy to create a warp bubble is both thrilling and daunting. The energy requirements, even with the most optimistic calculations, remain staggering. Yet, the fact that laboratory experiments have produced even the tiniest measurable warp in space-time has shifted the conversation from never to maybe someday. The focus now is on whether these effects can be scaled up from the nanoscopic to the macroscopic, and if so, how? One of the most promising avenues is the continued refinement of warp bubble geometry. When Miguel Alcubierre first published his warp drive concept, the energy needed was so immense that it seemed to close the door on any practical application. But Harold White and other physicists noticed that the original model used a simple, thick, walled spherical bubble for the sake of mathematical convenience. By reshaping the bubble into a toroidal or donut-like configuration and allowing the wall thickness to oscillate rather than remain static, the energy requirements could be slashed by several orders of magnitude. Instead of needing the mass energy of Jupiter, the revised models suggested that a few hundred kilograms of negative energy might suffice, still a huge challenge, but not outside the realm of future technology. Further refinements have continued to chip away at the numbers. Some research groups have proposed even more exotic bubble shapes, such as elongated ellipsoids or nested shells with varying densities. Each new configuration brings the theoretical energy requirements down a bit more. In some of the most recent papers, the amount of negative energy needed is measured in dozens of kilograms, provided the geometry is precisely optimized. These improvements are the result of mathematical ingenuity, not new physics. It's similar to how rocket engineers have improved efficiency over the decades by tweaking nozzle shapes and fuel mixtures. The underlying principles remain the same, but clever design can make a huge difference. A particularly exciting development is the idea that exotic matter might not need to be sustained continuously. Some models suggest that it could be possible to use ordinary energy to create brief, localized regions of negative energy density through quantum effects, maintaining them just long enough to generate thrust before letting them collapse and recreating them as needed. This pulsed warp drive concept would be analogous to how internal combustion engines work, burning fuel in cycles rather than all at once. If this approach is viable, it could shift the challenge from finding or creating exotic matter to developing precision engineering capable of controlling quantum effects on demand. The mathematics behind these optimizations have been checked and rechecked by independent physicists, and the consensus is that the numbers are sound. But as always, theory is only the first step. Whether these models can be realized in the real world remains to be seen. The leap from equations on paper to working hardware is enormous, and the universe may still have surprises in store that could render some or all of these ideas unworkable. Still, the progress from impossible to extraordinarily difficult is a meaningful one. Sometimes that's all it takes to keep the dream alive. Meanwhile, other researchers have taken different approaches to the problem. In 2002, Brazilian physicist José Netério proposed an alternative warp drive model that used a different mathematical trick to achieve similar results. The Netério drive, as it's now known, creates spacetime distortions through a modified tensor field configuration that some believe is more stable than Alcubierre's original design. The key difference is in how the warp bubble interfaces with normal space. Alcubierre's model creates sharp boundaries where space transitions abruptly from compressed to normal to expanded. These sharp edges require intense energy concentrations and might generate problematic radiation or gravitational effects. Netério's approach smooths out these transitions, distributing the space-time distortion more gradually across a larger volume. This is like the difference between a steep cliff and a gentle slope. Both change elevation, but the slope is easier to traverse and less likely to collapse. The smoother geometry could make the warp bubble more stable and less prone to quantum instabilities or spontaneous decay. It might also reduce secondary effects like Hawking radiation, which could be produced at the boundaries of a sharp-edged bubble. The energy requirements for the Netério drive are similar to those of the optimized Alcubierre models, but the engineering challenges are different. Instead of creating intense, localized warping, you need to generate a more diffuse but spatially extended distortion. This might actually be easier to achieve using Casimir-like effects or electromagnetic field manipulation, since you're not demanding extreme energy concentrations at specific points. The downside is that the mathematics becomes even more complex, involving advanced differential geometry and field theory. Most popular accounts of warp drives focus on Alcubierre's model simply because it's easier to visualize and explain. Some researchers have suggested that the best solution might combine elements from both models, using Netério's smooth boundaries for stability and Alcubierre's oscillating bubble walls for energy efficiency. Hybrid designs could offer the best of both worlds, and computer simulations are being used to explore the vast parameter space of possible configurations. The field is maturing from a single wild idea into a genuine area of study with multiple competing approaches, each with its own strengths and weaknesses. As the theoretical work continues, another intriguing question has emerged. If warp drives are possible, could we detect evidence that someone else in the universe has already built one? Gravitational waves, ripples in space, time caused by massive objects accelerating, are now routinely detected by observatories like LIGO and Virgo. These instruments are sensitive enough to measure distortions smaller than a proton's diameter, and they have already observed the mergers of black holes and neutron stars. A team of researchers in Germany recently proposed that a moving warp bubble should also generate a distinctive gravitational wave signature different from any natural astronomical source. They ran simulations to predict what these signals would look like and began searching existing gravitational wave data for matches. So far, nothing has turned up, but gravitational wave astronomy is still in its infancy. As detectors become more sensitive, it's possible that we might one day pick up the telltale sign of an artificial warp bubble moving through space, evidence that we are not the first to attempt this feat. The implications of such a discovery would be staggering. Not only would it prove that faster than light travel is possible, but it would also provide clues about how to build a working warp drive. The gravitational wave patterns would reveal information about the bubble's geometry, energy distribution, and propulsion method. It would be like finding a set of blueprints left behind by an advanced civilization, waiting for us to decipher them. The search for evidence of advanced propulsion in the universe is not limited to gravitational waves. If a civilization somewhere has mastered the art of warping space, their technology might leave other detectable traces. For instance, a warp bubble moving at extreme speeds through the interstellar medium could create shockwaves or emit unusual radiation. High-energy particles might be accelerated at the bubble's boundary, producing bursts of gamma rays or cosmic rays. Optical telescopes could look for the unique red and blue shifts in light that would occur around a moving warp field. So far, no confirmed detections have been made, but the universe is vast, and our instruments are only just beginning to scratch the surface. The idea of reverse engineering alien technology may sound like the stuff of science fiction, but history is full of examples where humans have learned from what others have built. When explorers encountered unfamiliar inventions, they often studied and eventually replicated them, even without fully understanding the underlying science at first. If we were to detect a warp drive signature from another civilization, it would give us a head start, direct observations of a working model in action. By analyzing the gravitational wave patterns, energy emissions, and other signatures, scientists could begin to deduce the principles behind the technology, much as engineers reconstruct internal workings of a device from its external behavior. This process would not be easy. An alien civilization capable of building warp drives might be thousands or even millions of years ahead of us. Their understanding of physics could include principles we have yet to discover. Still, the laws of nature are universal. If they have found a way to manipulate spacetime, those mechanisms should, in theory, be comprehensible to us once we have enough data. The challenge would be immense, but not insurmountable. After all, the basic rules of general relativity and quantum mechanics apply everywhere in the cosmos. Of course, there are risks. What if the signatures we detect reveal dangerous side effects? Perhaps warp bubbles destabilize space-time in ways that accumulate over time, or maybe they generate hazardous radiation. It's possible that advanced civilizations use warp drives sparingly or avoid certain regions of space to prevent unintended consequences. If we do find evidence of alien warp technology, we will need to proceed with caution, learning not just how to build such devices, but also how to use them safely. The connection between faster than light travel and time travel is another source of concern. According to relativity, moving faster than light could, under certain circumstances, allow for closed time, like curves, essentially paths through space, time that loop back on themselves. This raises the specter of paradoxes, such as the classic grandfather paradox, where a traveler could potentially prevent their own existence by altering the past. Some physicists argue that the universe must have built-in protections against such violations of causality, perhaps through unknown quantum effects or other mechanisms that prevent paradoxes from arising. Stephen Hawking famously proposed the chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel, even if the equations seem to allow it. In the context of warp drives, some theorists believe that the geometry of the bubble itself might act as a barrier, isolating the interior from external reference frames and preventing information from traveling backward in time. The energy required to maintain a warp bubble must be supplied in real time, and the bubble's boundary could act as a one-way membrane, enforcing causality and preventing paradoxes. Other models suggest that if time travel were possible, it might not allow changes to one's own past, but instead create new parallel timelines, a concept familiar from the many worlds. Interpretation of quantum mechanics. In this view, traveling back in time would simply branch the universe into a new reality, leaving the original timeline unchanged. While this idea is intriguing, it remains speculative, and no experimental evidence currently supports it. Regardless of the theoretical debates, the practical reality is that we have never built a warp drive or observed one in action. Until we do, questions about paradoxes and causality remain open. What is certain is that achieving faster than light travel would revolutionize our understanding of the universe and force us to confront some of the deepest mysteries in physics. One of the most profound challenges of near-light speed travel using conventional propulsion is time dilation. As an object approaches the speed of light, time slows down for it relative to stationary observers. At 99% of light speed, time passes 7 times slower for the traveler than for those left behind. This means that a 10-year journey for the crew would correspond to 70 years on Earth. The so-called twin paradox illustrates this. Identical twins, one traveling at high speed and the other remaining on Earth, would age at different rates. The traveling twin would return younger, having experienced less time. This effect is not just theoretical. It has been confirmed in particle accelerators, where unstable particles moving at relativistic speeds decay more slowly than their stationary counterparts. For interstellar missions, time dilation creates a cruel dilemma. The crew might reach another star within their own lifetimes, but everyone they knew on Earth would have aged or passed away. The psychological and social consequences of such journeys would be profound. Generation ships, which accept the reality of multi-generational travel, sidestep the problem of time dilation but introduce new challenges. Maintaining a stable society over centuries, preserving mission focus, and preventing technological or cultural drift are all daunting tasks. The isolation from Earth would be total, and the original mission objectives could be lost over time. Warp drives, if they work as theorized, offer an elegant solution, because the ship inside the bubble is not actually moving through space at relativistic speeds. Time dilation does not occur. Time flows at the same rate inside the bubble as it does on Earth. This means that travelers could journey to nearby stars and return without experiencing the temporal disconnect that plagues conventional high-speed travel. Relationships, knowledge, and culture would remain synchronized, making interstellar missions far more feasible from a human perspective. This advantage extends beyond personal experience. For governments, corporations, and scientific organizations, the ability to conduct missions on timescales measured in years or decades, rather than centuries, makes interstellar exploration and colonization economically and logistically viable. The lack of time dilation also helps avoid causality issues, as events inside and outside the bubble remain in proper sequence. Of course, all of this depends on the warp bubble functioning as predicted. If unexpected side effects on time or causality emerge, new solutions will be needed. But according to current models, warp travel could provide not just speed, but a way to maintain our connection to home, history, and each other as we venture into the stars. Another major obstacle to interstellar travel using conventional propulsion is the problem of acceleration. To reach even a small fraction of light speed within a human lifetime, a spacecraft would need to accelerate at rates far beyond what the human body can withstand. Astronauts during launch experience about 3 times Earth's gravity, and fighter pilots can briefly endure up to 9 times gravity before losing consciousness. But to accelerate to a significant percentage of light speed in a reasonable time frame would require sustained forces that would crush any living organism. Bones would shatter, organs would rupture, and the brain would be irreparably damaged. Even the most advanced acceleration couches or liquid immersion systems, designed to distribute forces more evenly, would be useless at the extreme accelerations required for rapid interstellar travel. Some science fiction stories propose generation ships that accelerate very slowly, spreading the force over decades so that the crew never feels more than a gentle push. While this avoids the lethal effects of high acceleration, it means the journey will take centuries or longer, and the original travelers will never see their destination. Suspended animation or cryogenic sleep is another popular idea, but freezing and reviving humans without damage remains beyond our current capabilities. Even if we could perfect such technology, it would not solve the fundamental problem of how to accelerate a ship quickly and safely. Warp drives, by contrast, offer a solution that sidesteps the issue entirely. Inside a warp bubble, the spacecraft and its occupants are not actually accelerating through space. Instead, space itself is being manipulated around them. The ship remains stationary relative to its local spacetime, experiencing no inertial forces. There is no sensation of movement, no crushing acceleration, and no need for special life support systems to protect against high G forces. The transition from rest to faster than light travel would be imperceptible to those inside the bubble. You could go from 0 to 10 times the speed of light instantly, and your coffee wouldn't even ripple in its cup. This unique property of warp travel opens up possibilities that are simply unattainable with conventional propulsion. Fragile equipment, delicate biological samples, and even entire ecosystems could be transported without risk of damage from acceleration. Interstellar colonization becomes much more feasible when you can move not just people, but plants, animals, and microorganisms in a self-sustaining environment. With traditional rockets, keeping such a system alive during decades of travel and violent acceleration phases would be nearly impossible. With a warp bubble, it becomes routine. The interior of a warp bubble would feel completely ordinary. Physics inside the bubble would be the same as on Earth. Time would pass at the usual rate. Gravity would be determined by whatever artificial systems you installed, and all the familiar laws of chemistry and biology would apply. The extreme warping of space-time occurs only at the boundary of the bubble, creating a protective shell around the ship. This isolation from the external universe has some interesting consequences. For one, communication with the outside world could be challenging. Radio signals and other forms of electromagnetic radiation might not be able to cross the bubble's boundary, effectively cutting off the ship from real-time contact with Earth during transit. Mission planners would need to account for these blackout periods, ensuring that crews have all the information and autonomy they need before departure. Navigation would also be different. Looking out a window, the view would be distorted by the warping of space-time. Light from stars ahead would be blue-shifted, compressed into higher frequencies, while light from behind would be redshifted, stretched into lower frequencies. Some models suggest that the view forward might be completely black, as the compressed space in front of the bubble could act like an event horizon, preventing light from reaching the ship. Despite these oddities, the environment inside the bubble would remain stable and safe. The bubble's boundary would shield the ship from cosmic radiation, interstellar dust, and other hazards. You could, in theory, pass through a supernova or a dense asteroid field without harm, as the bubble would deflect or absorb any external threats. The only gravity inside would be what you create artificially, since the warp field itself does not generate internal gravitational effects. The energy systems required to power the warp drive would operate normally from the crew's perspective. Fusion reactors, antimatter containment, and power distribution networks would all function as designed. The exotic physics needed for the warp bubble would be confined to the boundary, where space-time transitions from normal to warped states. This means that, for the most part, life inside the bubble would be as comfortable and predictable as life on Earth. Of course, the psychological effects of such a journey should not be underestimated. Being isolated in a pocket of normal reality, cut off from the rest of the universe while traveling at unimaginable speeds, could be unsettling. Some crew members might experience anxiety or disorientation, knowing that they are surrounded by a shell of warped space-time. Others might find it comforting, a safe haven in the vastness of space. Training and preparation would be essential to ensure mental health and mission success. The real challenge, however, remains building a warp drive in the first place. While the interior of the bubble would be familiar and safe, creating and maintaining the bubble itself is a monumental task. The energy requirements, though reduced by recent theoretical advances, are still far beyond what we can currently achieve. Generating and controlling negative energy density, shaping the bubble's geometry, and scaling up from nanoscopic laboratory effects to a full-size spacecraft are all hurdles that must be overcome. Despite these obstacles, research continues. NASA has advanced propulsion labs, led by figures like Harold White, have quietly pursued warp drive concepts for years. Their work involves measuring tiny spacetime distortions, experimenting with Casimir effects, and simulating optimal bubble geometries. While much of this research is preliminary and sometimes classified, it represents a serious effort to turn science fiction into reality. Other organizations are also getting involved. Private companies with deep pockets and a passion for space exploration, such as SpaceX and Blue Origin, are rumored to be investigating exotic propulsion methods. Their resources, engineering talent, and willingness to take risks could accelerate progress. International collaboration is limited by security concerns, but the race to develop faster than light travel is no longer confined to government labs. The path forward is uncertain, but the potential rewards are enormous. If we can solve the technical challenges, warp drives could transform humanity's relationship with the cosmos. The dream of reaching the stars within a single lifetime would move from fantasy to possibility, opening up new worlds and new futures for our species. The pursuit of warp drive technology is no longer just a government endeavor. In recent years, private industry has begun to take a keen interest in advanced propulsion, recognizing both the commercial and scientific potential of breaking the light speed barrier. Companies like SpaceX, led by Elon Musk, have made no secret of their ambitions to make humanity a multi-planet species. While their public focus remains on Mars colonization and reusable rockets, there are persistent rumors and subtle hints that their research and development teams are quietly exploring propulsion concepts that go far beyond chemical rockets. SpaceX's culture of rapid prototyping and willingness to tackle high-risk, high-reward projects makes it a natural incubator for revolutionary ideas. The company's hiring patterns, equipment acquisitions, and occasional cryptic job postings suggests that they are at least keeping an eye on the latest developments in theoretical physics. Some former employees, bound by non-disclosure agreements, have hinted at research into space-time manipulation and quantum field effects, though details remain tightly guarded. The company's vast resources, combined with Musk's personal fortune and appetite for bold ventures, mean that if a breakthrough in warp technology is possible, SpaceX could be among the first to pursue it seriously. Blue Origin, founded by Jeff Bezos, is another major player in the private space race. While their public messaging is more conservative, focusing on lunar landers and orbital tourism, their advanced concepts teams are staffed with physicists and engineers who have the expertise to explore exotic propulsion. The company's long-term vision of millions of people living and working in space would be dramatically accelerated by any technology that could shrink interstellar distances to manageable timescales. Other aerospace giants, such as Lockheed Martin, Boeing, and Northrop Grumman, maintain advanced research divisions that quietly investigate next-generation propulsion. These companies have long-standing relationships with government agencies and access to classified research, giving them a unique vantage point. Their work is often shrouded in secrecy, but patent filings and conference presentations occasionally reveal glimpses of their interests in space, time engineering, and quantum effects. Beyond the established players, a new wave of private research initiatives is emerging, often funded by tech billionaires with a passion for space and a willingness to invest in long-shot ideas. Yuri Milner's breakthrough initiatives, for example, has already funded projects aimed at detecting extraterrestrial life and developing laser-propelled probes for interstellar missions. The Breakthrough Starshot project envisions sending tiny spacecraft to Alpha Centauri at a significant fraction of light speed using powerful ground-based lasers. While this approach is still rooted in conventional physics, it demonstrates the appetite for radical innovation in the private sector. Private research has certain advantages over government programs. It can move faster, take greater risks, and avoid some of the bureaucratic and classification hurdles that slow down public projects. However, it also faces challenges, such as limited access to the most advanced government facilities and the need to protect intellectual property. The ideal path forward may involve partnerships between public and private entities, though issues of national security and commercial competition can complicate such collaborations. As the race to develop warp technology heats up, three main approaches have emerged as the leading contenders. The first is the Alcubierre drive, which remains the most famous and widely studied. This concept relies on creating a bubble of space-time that contracts in front of the ship and expands behind it, allowing the bubble to move faster than light relative to the surrounding universe. Recent theoretical work, especially by Harold White and his team, has focused on reducing the energy requirements by optimizing the bubble's shape and exploring ways to generate negative energy density using quantum effects like the Casimir effect. The second approach is the Netario drive, which offers potential improvements in stability and safety. By smoothing out the transition between normal and warped space, the Netario model reduces the risk of quantum instabilities and may be easier to realize using electromagnetic fields or plasma configurations. Some researchers are investigating whether advanced plasma containment systems, similar to those used in fusion reactors, could be adapted to generate the necessary spacetime distortions. The third, and perhaps most speculative, approach involves harnessing dark energy directly. Dark energy makes up about 70% of the universe's total energy content and is responsible for the accelerated expansion of the cosmos. It exhibits negative pressure, a property that seems tailor-made for warp drive applications. If scientists can learn to manipulate or concentrate dark energy locally, it could provide the exotic fuel needed for faster than light travel without requiring the creation of negative mass or the amplification of tiny quantum effects. The challenge is that dark energy remains one of the least understood phenomena in physics, and current theories offer little guidance on how to control it. Some theorists propose hybrid models that combine elements from all three approaches. For example, a warp drive might use the energy, efficient geometry of the Alcubierre model, the stability of the Notario configuration, and the fuel source provided by dark energy manipulation. Computer simulations are being used to explore the vast landscape of possible designs, searching for combinations that minimize energy requirements, maximize safety, and offer practical engineering pathways. Laboratory experiments are still far behind the simulations, as generating and measuring space-time distortions at even the millimeter scale remains a formidable challenge. The instruments needed to detect such effects are at the cutting edge of current technology, and scaling up from nanoscopic to macroscopic levels will require entirely new breakthroughs in materials, science, quantum engineering, and energy generation. Despite these hurdles, progress is being made. Each successful experiment, no matter how small, validates aspects of the theory and points the way forward. Each simulation that identifies a promising configuration helps focus research efforts and avoid dead ends. The field is moving from pure speculation toward practical engineering, and the diversity of approaches increases the odds that someone, somewhere, will find a solution that works. Ultimately, the quest for warp drive technology is forcing scientists and engineers to grapple with the deepest mysteries of the universe. It is a journey that requires not just technical skill, but also imagination, persistence, and a willingness to challenge the boundaries of what is considered possible. The next great leap in human exploration may come not from building bigger rockets, but from learning to shape the very fabric of reality itself. The pursuit of warp drive technology is pushing the boundaries of our understanding of physics, especially at the intersection of general relativity and quantum mechanics. For centuries, classical physics described the universe as a predictable machine where every action had a clear cause and effect, and the future could be calculated if you knew the present well enough. But the quantum revolution shattered that certainty, revealing a world where particles can exist in multiple states at once, and where the very fabric of space is alive with uncertainty and fluctuation. At the heart of warp drive research lies the challenge of manipulating quantum vacuum energy, the restless sea of virtual particles that pop in and out of existence even in the emptiest regions. Space, the Casimir effect, which demonstrates that the energy density between two closely spaced metal plates can be lower than the surrounding vacuum, is a direct consequence of this quantum foam. While the effect is tiny and only measurable at nanoscales, it proves that negative energy densities are not just theoretical curiosities, but real physical phenomena. Scaling up the Casimir effect, or similar quantum phenomena to the level required for a warp bubble, is a monumental task. The force drops off rapidly as the distance between plates increases, and creating significant negative energy densities over macroscopic distances would require new materials or technologies that do not yet exist. Some researchers are exploring the use of metamaterials, engineered substances with properties not found in nature, to manipulate electromagnetic fields and vacuum energy in novel ways. Others are investigating whether quantum computers, which exploit the same strange properties of quantum mechanics, could help simulate and eventually control the complex interactions needed to generate a warp field. Quantum entanglement, another bizarre feature of the quantum world, is also being considered. Entangled particles can influence each other instantaneously, no matter how far apart they are, a phenomenon Einstein famously called spooky action at a distance. While entanglement does not allow information to travel faster than light, some theorists wonder if it could play a role in coordinating the quantum effects required for a stable warp bubble, or in enabling communication between the inside and outside of the bubble despite the space-time barrier. The transition from classical to quantum thinking is not just a technical challenge, but a philosophical one. It requires accepting that the universe is fundamentally probabilistic and that our intuitions, shaped by everyday experience, may not apply at the deepest levels of reality. Warp drive research is forcing scientists to confront these mysteries head on as they attempt to engineer effects that have so far only been observed in the most controlled laboratory conditions. One of the most tantalizing possibilities is that dark energy, the mysterious force driving the accelerated expansion of the universe, could be harnessed for warp propulsion. Dark energy makes up about 70% of the universe's total energy content, yet we know almost nothing about its true nature. It appears to have negative pressure, which is exactly the property needed to create the spacetime distortions required for a warp bubble. If dark energy could be concentrated or manipulated locally, it might provide the exotic fuel that has so far eluded researchers. The idea of tapping into dark energy sounds like science fiction, but history is full of examples where practical application preceded full theoretical understanding. Humans used fire, breadcrops, and built machines long before they understood the underlying chemistry, genetics, or physics. It is possible that the first working warp drive will be built by engineers who have learned to manipulate dark energy or quantum vacuum effects through trial and error, with the theory catching up later. Detecting and measuring dark energy at laboratory scales is a major challenge. We know it exists because of its effects on the expansion of the universe, but its local properties are incredibly subtle. Some researchers propose looking for its influence in gravitational wave data or in the behavior of quantum systems under extreme conditions. If we can learn to map dark energy distributions or identify regions where it behaves differently, we might discover natural seams in space-time where manipulation is easier. The concept of space-time as a smooth, continuous fabric is a useful approximation, but quantum mechanics suggests that at the smallest scales, it may be grainy or pixelated. The Planck length, about 1035 meters, is thought to be the smallest meaningful distance, below which the very concept of space and time breaks down. Some theories propose that space-time is woven from discrete loops or networks, and that these structures could be manipulated to create the effects needed for a warp drive. Black holes and wormholes provide natural laboratories for studying extreme space-time curvature. The event horizon of a black hole marks a boundary where the rules of physics change dramatically, and quantum effects like Hawking radiation emerge. Wormholes, if they exist, would be shortcuts through space-time held open by exotic matter with negative energy density, the same ingredient needed for a warp bubble. Studying these phenomena could provide clues about how to engineer artificial space-time boundaries. String theory, another leading candidate for a theory of everything, suggests that space-time has additional dimensions beyond the familiar three of space and one of time. These extra dimensions are usually hidden, but at high energies or in regions of extreme curvature, they might become accessible. If warp drives operate by manipulating these hidden dimensions, they could open up entirely new avenues for research and technology. All of these ideas remain highly speculative, but the potential rewards are enormous. If we can learn to manipulate the fundamental structure of space-time, we could not only achieve faster than light travel, but also unlock new forms of energy, communication, and computation. The universe may be far more malleable than we ever imagined, and the key to the stars could be hidden in the quantum foam that underlies all of reality. The journey from theory to practice will not be easy. It will require breakthroughs in physics, engineering, and materials science, as well as new ways of thinking about the universe. But the progress made so far, from the first mathematical models to the creation of microscopic warp bubbles in the lab, suggests that the dream of interstellar travel is not as far-fetched as it once seemed. The next great leap may come from an unexpected direction, as researchers continue to push the boundaries of what is possible. As our understanding of the universe deepens, the concept of manipulating space-time for practical purposes becomes less of a fantasy and more of a scientific challenge. The mysterious nature of dark energy, which makes up the majority of the cosmos, remains one of the greatest puzzles in modern physics. We know it's there because it's causing the universe to expand at an accelerating rate, but its true nature is elusive. Some theories suggest it's a property of the vacuum itself, a kind of energy woven into the fabric of space-time. Others propose it's a dynamic field, changing over cosmic time. Regardless of its origin, dark energy's negative pressure is exactly the kind of exotic property that warp drive concepts require. If we could learn to manipulate dark energy, even in small, localized regions, it might provide the fuel for warp bubbles without the need for impossible quantities of negative mass. The challenge is that, so far, we have no way to detect or control dark energy on laboratory scales. Its effects are only noticeable across billions of light years, making it like trying to measure a gentle breeze in the middle of a hurricane. Some researchers are developing new sensors and experimental setups to look for subtle signatures of dark energy in gravitational wave data or in the behavior of quantum systems under extreme conditions. If we could map its distribution or find places where it naturally concentrates, we might discover shortcuts to manipulating space-time. The idea that space-time itself might have a hidden structure is gaining traction. Quantum gravity theories, such as loop quantum gravity and string theory, suggest that the smooth fabric described by Einstein is actually made up of tiny, discrete units, like the threads in a tapestry or the pixels on a screen. At the Planck scale, space-time might be granular, with natural seams or boundaries where the rules change. If these seams exist, they could be the weak points where it's easiest to bend or fold space, much like a tailor cuts along the grain of fabric. Black holes, with their event horizons and singularities, are the most dramatic examples of space-time boundaries, and studying them could reveal how to create artificial boundaries for warp bubbles. Wormholes, if they exist, would be the ultimate shortcut, tunnels through space-time connecting distant regions. Theoretical models suggest that keeping a wormhole open would require exotic matter with negative energy density, the same ingredient needed for warp drives. Some physicists speculate that a warp bubble is essentially a mobile, self-contained wormhole, carrying a pocket of normal space through the universe. If we could learn to create and stabilize such structures, interstellar travel would become a matter of engineering rather than pure speculation. String theory adds another layer of complexity, proposing that space-time has extra dimensions beyond the familiar three of space and one of time. These hidden dimensions are usually curled up too tightly to detect, but under extreme conditions, they might become accessible. If warp drives could tap into these extra dimensions, they might achieve effects that are impossible in ordinary four-dimensional space-time. The mathematics is daunting, but the potential payoff is enormous. Cosmic strings, hypothetical defects in space, time left over from the early universe, could provide natural laboratories for studying these effects. These one-dimensional objects, if they exist, would have immense mass and could stretch across galaxies. If we could find and study a cosmic string, it might reveal how space, time can be manipulated on a grand scale. Alternatively, we might learn to create artificial analogs in the lab using advanced materials or quantum fields. Despite the speculative nature of much of this research, the progress made in recent years is encouraging. The detection of microscopic warp bubbles in laboratory experiments, the ongoing refinement of theoretical models, and the growing interest from both public and private sectors all suggest that dream of faster than light travel is moving closer to reality. The remaining challenges are formidable, but not insurmountable. One of the biggest hurdles is energy generation. Even with optimized bubble geometries and reduced requirements, the power needed to create and sustain a warp bubble is immense. Current fusion research is making steady progress, but we have yet to achieve sustained net energy gain. Antimatter production is still slow and expensive, and dark energy manipulation remains purely theoretical. Creating negative energy density at useful scales is perhaps the hardest problem of all. While Harold White's team has detected nanoscopic warp geometry, scaling up by many orders of magnitude will require breakthroughs in both physics and engineering. Materials science is another critical area. Any spacecraft surrounded by intense warp fields would be subjected to stresses and radiation, unlike anything encountered in conventional spaceflight. The structure must remain stable while space-time warps violently just meters away. Developing materials that can survive these conditions will require extensive testing and likely the invention of entirely new classes of substances. Navigation and control present their own set of challenges. Steering a ship that isn't moving through space in the traditional sense, but is instead riding a wave of warped space-time, will require new kinds of sensors and guidance systems. Avoiding collisions at faster than light speeds, handling emergencies inside the bubble, and ensuring safe transitions in and out of warp will all demand innovative solutions. Theoretical physics still has gaps that make predictions uncertain. We cannot yet fully simulate the dynamics of a warp bubble, especially when quantum effects are included. Whether dark energy will help or hinder remains unknown. Each of these uncertainties could hide shows, stopping problems that only become apparent during actual construction and testing. International cooperation could accelerate progress, but security concerns and competition make open collaboration difficult. If a breakthrough occurs in a classified program, it may be years before the wider scientific community learns of it. Funding is another limiting factor. Warp drive research currently operates on a shoestring compared to other big science projects. If humanity committed resources on the scale of the Apollo program or the Manhattan Project, the timeline for practical warp drives could shrink dramatically. History shows that technological revolutions often happen faster than expected once key discoveries are made. The leap from the first powered flight to routine air travel took just a few decades. Nuclear energy went from theory to reality in less than 10 years. The right breakthrough in negative energy generation, dark energy manipulation, or space-time engineering could trigger a similar explosion of progress in warp technology. But it's also possible that some barriers will prove more stubborn. Fusion power has been 30 years away for over half a century. Quantum computing took decades longer than early optimists predicted. Warp drives may fall into either category, sudden revolution, or slow, incremental progress. The only way to find out is to keep pushing the boundaries, funding research, and encouraging creative thinking. The stakes are high. Faster than light travel would not just be a technical achievement, it would fundamentally change what it means to be human. The stars would no longer be distant points of light, but reachable destinations. Our place in the universe would be transformed, and the possibilities for exploration, discovery, and survival would expand beyond anything our ancestors could have imagined. The promise of warp drive technology is not just about speed, it's about redefining humanity's future. If we succeed in mastering the manipulation of spacetime, the entire galaxy could open up to us. Hundreds of potentially habitable planets within 50 light years would become accessible, turning what are now unreachable points of light into real destinations. Colonies could be established on worlds far more suitable for life than any planet in our solar system. Humanity would no longer be a single planet species vulnerable to extinction from a single catastrophic event. Instead, we would become a civilization spread across multiple star systems, resilient and adaptable in ways we can barely imagine today. The economic implications of such a leap are staggering. Asteroid mining would become routine as warp. Capable ships could travel to the asteroid belt and back in hours or days. Resources that are rare or depleted on Earth could be sourced from other solar systems, fundamentally altering the global economy. Energy, minerals, and even biological resources from alien worlds could be brought home, fueling new industries and scientific revolutions. The scale of wealth and opportunity would dwarf anything in human history. Scientific discovery would accelerate at an unprecedented rate. Instead of relying on telescopes and remote sensing, researchers could visit exoplanets directly, study alien ecosystems up close, and observe cosmic phenomena firsthand. The mysteries of planetary formation, the origins of life, and the nature of black holes and neutron stars could be explored not just through theory, but through direct experimentation and observation. Every new world would offer surprises, challenging our assumptions and expanding our understanding of the universe. The possibility of encountering extraterrestrial life would become much more real. Instead of waiting centuries for radio signals to cross the void, we could send missions to nearby star systems and search for life directly. We might find evidence of ancient civilizations, thriving alien biospheres, or even intelligent beings with whom we could communicate face to face. The philosophical, cultural, and ethical implications of such encounters would be profound, forcing us to rethink our place in the cosmos and our responsibilities as explorers. Culturally, the expansion into the galaxy would transform humanity in ways that are difficult to predict. Isolated colonies would develop their own customs, languages, and societies, shaped by the unique conditions of their new worlds. Over generations, these differences could become as significant as those that once separated continents on Earth. Alternatively, rapid travel and communication enabled by warp technology might help maintain a sense of unity, allowing ideas, art, and knowledge to flow freely across the stars. Either way, the diversity and richness of human experience would multiply. Of course, such power comes with risks. The ability to travel faster than light could be weaponized, giving unprecedented strategic advantages to those who control the technology. Space warfare could erupt on scales that make terrestrial conflicts seem trivial. The environmental impact of repeated warp travel is unknown. Could it destabilize regions of space-time, create dangerous radiation, or leave behind forms of pollution we don't yet understand? These are questions that must be addressed before the technology is widely deployed. Ethical dilemmas would also arise. Who gets access to warp ships? How do we prevent the exploitation of new worlds and their resources? If we encounter primitive life, do we have a duty to protect it, or do we risk repeating the mistakes of colonialism on a cosmic scale? The rights of future colonists the governance of interstellar societies, and the preservation of Earth's heritage would all become pressing issues. These challenges demand careful thought and international cooperation, not just technological prowess. The psychological impact of interstellar travel should not be underestimated. The knowledge that we are no longer confined to one planet, that the stars are within reach, would fundamentally change how we see ourselves. It could inspire a new era of optimism and ambition, much as the Apollo program did in the 20th century, but on a far grander scale. The sense of possibility would be limitless, motivating generations to dream bigger and strive harder. This moment in history, as researchers inch closer to making warp drive a reality, may one day be seen as the turning point when humanity's destiny changed forever. Whether we succeed or fail, the attempt itself is valuable. The technologies developed along the way, advances in energy, materials, computation, and our understanding of the universe, will have countless applications, improving life on Earth even if we never leave it. The scientists and engineers working on these problems today are pioneers, pushing into unknown territory. Their work may not bear fruit for decades, but it lays the foundation for future breakthroughs. The next great discovery could come from anyone: a physicist who finds a new way to generate negative energy, an engineer who invents a stable warp field generator, or a programmer who writes code that makes real-time warp navigation possible. The universe is vast, and the solutions we seek may be hidden in places we haven't yet thought to look. Even if warp drives never allow us to cross the entire universe, they would still transform what is possible within our cosmic neighborhood. The observable universe is so large that even at 1,000 times the speed of light, it would take millions of years to traverse. But the nearby stars, with their billions of planets, would finally be within our reach. That is the true promise of this technology, not infinite power, but the ability to explore, to learn, and to survive. The race to achieve faster than light travel is about more than science or national prestige. It is about whether humanity will remain forever confined to a single world, or whether we will take our place among the stars. The future is being written now in laboratories and workshops around the world by people who refuse to accept the limits of the present. Each experiment, each equation, each new idea brings us closer to a day when the impossible becomes routine. Perhaps you or someone you know will be the one to make the break through that changes everything. The universe is waiting, and the next chapter of human history is ready to be written, one discovery, one journey, one leap at a time.